Welcome everybody. I hope if this is one of the last topics of the day, you're not so tired to go through a lot of formulas and matrix computations. Sorry. So yeah, just a little thing about me. I am an electrical engineer from Universidad de Antioquia. I am original from Colombia. So yeah, most of the work I did back in electrical engineering was related to signal processing and digital image processing. Then I went to Columbia University where I did my master's in applied mathematics. I was like mostly focused on computational science and engineering, doing a lot of numerical analysis and numerical linear algebra. And now I'm working as an applied scientist at the CAR Labs. We are a geospatial analytics company. So as Garrett mentioned, my focus is on maritime intelligence. I basically create a lot of products derived from ocean transportation, data products for ocean transportation based on remote sensing and satellite imagery and other different kind of sensors. And I have to spend a lot of my time worrying on how to process all these remote sensing data efficiently. Since we have global coverage, we have lots and lots of pixels and time series data to process. So I have to spend a lot of my time worrying about these kind of problems at large scale. Sorry. So why are we talking about linear algebra and deep learning today? So all the deep learning primitive operations at its core, they depend heavily on linear algebra. So as I saw this tweet a while ago from the Brooklyn Institute, and it's like machine learning is just a scientist tool. A lot of it is just nicely packaged linear algebra. So this is a very true statement, since even though deep learning and neural networks can handle like very, very non-linear problems, if you start decomposing all the operations you are making on each layer of a deep neural network, you realize that each of them is just a linear algebra operation. You can call it a convolution or fully connected layer, whatever you want to call it. It is gonna be always rely on linear algebra. So so for deep learning algorithms, we need algorithms that make linear algebra algorithms that make computations especially fast. So why, again, what are we talking about linear algebra here? Like weights, inputs and outputs in neural networks are stored in tensors, and these tensors are just ND arrays, not tensors as in physics, but tensors as in ND arrays. Tensors is just a fancy way to call them. So what are the primitive operations we have here? As I mentioned before, matrix multiplication is everywhere. Convolution is everywhere in convolutional networks. Inner product transposition and rectify linear units, all of them depend on linear algebra operations. So matrix multiplication, let's start with why is this a fundamental task? So if you are multiplying two matrices and they are square matrices of the same dimensions, you can naively implement an algorithm that is ON to the 3, which is really high if our sizes of our matrices is really, really big. So there are some algorithms like a Strassen algorithm that it's super complicated and it brings down the complexity from n cubed to n 2.8. So it is a big improvement, and I quote big improvement, but this algorithm is rarely implemented because it's just too complex to implement at scale. So I wanted to highlight these top 10 algorithms of the 20th century. One of these algorithms is the start or the foundation of the decompositional approach to matrix computations. It was back in 1951 by Householder. And it's just the ability to represent a matrix into a lower triangular, diagonal, orthogonal matrix. And these forms have shown to be extremely useful because it not only accelerate the matrix computations, but also it helps to reduce the size of your models. So when this was first introduced, it was just basically LU decomposition. However, after this, there was like many different decompositions that came after 1951, like the QR decomposition, singular value decomposition, many other decompositions that we're going to focus just in one here, but it's just to highlight the importance of this very classical algorithm back in the 50s and how important it is for today's deep learning networks. So just to recap what singular value decomposition is. So this algorithm is ubiquitous in deep learning and signal processing. So the whole idea is to take one matrix with high rank, and we're gonna recap what rank is. So we decompose a matrix into low rank matrices. So if you don't remember, the rank of a matrix is basically the number of linearly independent columns that we have and the space that these linear independent columns can span. So as I mentioned before, when we decompose, approximate a matrix with high rank to a low rank matrix, then we reduce the model size, and we also take advantage of sparsity. When we have input matrices or input tensors with many different features, so there's a lot of sparsity. So it actually optimizes the model size by taking advantage of sparsity. When you find the singular values of these sparse matrices, there's a lot of very small singular values, and those are the ones that we're gonna take out because they don't contribute to information in our data. So this is the summary of what singular value decomposition is. So let's say that we have a matrix A. In this case, it's just going to be a real matrix n by n. And then we know that we can factorize this matrix as U sigma V transpose, where U is going to be an n by m matrix, which are each column is equivalent to each eigenvector of A transpose. V is going to be n by n, and it's going to be each column is going to be eigenvectors of A transpose A, and sigma is going to be a diagonal matrix where all elements in the diagonal are going to be the singular values of A transpose A, and they are going to be ordered from the max value to the mean value. So if you see here, this matrix has R, a number of singular values, and R, as we saw before, is going to be the rank of our matrix. So basically, we want to factor our original matrix A this way. And then after we have this decomposition, we want to find a value V here that is larger than 0 and less than the original rank of the matrix to find a V rank or a low rank approximation to our matrix. So we see here our A sub B approximation is going to be basically the multiplication of the first V singular values with the corresponding eigenvectors. So we really want to find like a sweet spot of V value or the low rank approximation such that the norm, the matrix norm of the difference between the original and the approximation is minimized. So we saw before that our original naive approximation, complexity for matrix multiplication was n cubed, or if we have m by k, k by n, it would be complexity O m k n. But when we find a low rank approximation, we can accelerate these almost to linear time after we find our low rank approximation. I think there's a mistake here. Instead of this R, it should be a V, because V is the low rank approximation or the number of main components we're getting from our original matrix. So just to show an example of how it looks in real life. So this here is a scene from a GO-16 satellite, and it corresponds to the blue band, which represents reflectance from atmosphere. So in this specific sample, we have a matrix representation of this image. It's gonna be M by dimension M is equals to N equals to 1000. And the rank of this matrix, the number of independent columns in this matrix is going to be 844. So that means that there are some few, like 100 something vectors, column vectors that are not linearly independent, that can be represented as a linear combination of the other ones. So they don't really add any value or any information to my matrix representation. So we want to compare here how, if I perform a singular value decomposition of my original image on the left, and I just take my first 15 singular values. So this is how it looks. So it doesn't look very clear. However, when we are training neural networks, and this is going to be my input information, we already know that input data doesn't have to be like super accurate or super high resolution, because there's going to be still a lot of approximations, and input data doesn't have to be perfect. So if we approach here with our k equals to 15, so we are gonna have something like this, the image we see in the left. If we increase this to a 3D rank matrix, so we have something that it's really good. And it really depends on the application you are working on. If you have something like, in our specific case, we want to do probably a pixel by pixel classification if we want to identify if it's a cloud or it's a cloud shadow, or we just want a cloud mask that says this pixel is a cloud, this pixel is not a cloud. So the image in the right with the rank of 30 instead of 844, it's good enough. So that's something that we use SVD for, to generate low rank approximation of our input data. However, it can also be used for things like weight matrices. So when you have a fully connected layer, your weight matrices are really big too. So after let's say after one pass, after you initialize randomly your weights, and after the first pass, you also want to apply singular value decomposition to your weight matrices. We don't want to apply SVD on random matrices, random initialization of weights, because it's going to give us, it doesn't have a lot of information because it's random, and it gives us back a lot of small singular values. So the preference for us is just use one pass with full rank matrices for our weights, and after weights are starting to be optimized, we can then use SVD to minimize the rank of the weight matrices. However, what's the problem of classical SVD? For big matrices, all these operations that we saw before are they could require a relatively large rank for approximating your data really well and to minimize the error. And these at scale, the algorithm can be very slow. So there's a lot of randomization algorithms that you can apply on big data. I mean, when I say big data, it has to be big data, not like this 1000 by 1000 matrix, but way bigger data in the order of hundreds of thousands. So randomization on this kind of algorithms has shown very good results. And there are like some tricks or like parameters that you have to be very careful about. But once you have found your sweet spot, these kind of randomized algorithms work really well. So what we're gonna do first, we want to specify in advance what is the rank of the problem I want to solve. So you specify your target rank K, you have your matrix A, R, n by n, and then you're gonna pick an oversampling parameter, P. So you're gonna use this parameter just to sample your original matrix. And then you're gonna perform SVD on the sample matrix, not your original matrix. So we want to build this matrix Q here, which is M by K plus P, where K is my target rank and P is my oversampling parameter, such that we can minimize the norm of this difference that we see here. Or not only minimize, that we can find this error is bounded. That's very important because we want our algorithms to converge, and if this is not bounded, it can exploit at some point. So it's really important that the error is bounded. So the first question that comes to mind is, what is the optimal value for P for my oversampling parameter to minimize the loss of information? So there's a lot of literature how to choose the P parameter and how to choose the sampling algorithm itself. You could just generate independent IID samples from your matrix using like a different kind. It can be just random, or it can be drawn for some distribution. But what the algorithm we're going to show here is where we want to approximate A to a rank 2K. So P is equals to K. And we find that we can definitely, the expected value of the difference of my original matrix and my decomposed matrix is bounded by the expression that we see here. So we see that at the end, this is going to be bounded by the K plus 1 singular value. And when we have this type of matrices, when my singular values are decaying fastly, so this error can be very minimal. So this 1/3 here that we see, it's really when I pick P equals K. This really helps us. I mean, if you start picking a larger P, of course, this exponent here is going to be smaller, and my error is going to be smaller and smaller. But at the same time, then I am taking more like a bigger matrix. And the idea is that we want to find a sweet spot where the matrix approximation is good enough, but my error is bounded, and at the same time is small. So for the rest of the presentation, we're going to pick 2K rank approximation. So the algorithm can be performed in 2 stages. One stage is we're gonna basically generate a Gaussian 2K. So this is how S matrix refers how we're gonna sample our original matrix. We're gonna sample using a Gaussian distribution, and we're gonna pick this number of columns here. So then we're gonna find this product Y, which is A transpose to the Q. This Q parameter is chosen to be just 1. It could be 2, but for the algorithm is chosen to be 1. Omega here. And then we want to construct a matrix Q whose columns are an orthonormal basis for the range of Q. So this Q matrix is going to have rank 2K. Then it's a complex algorithm, and probably you're wondering why I am bothering doing all these steps that are already too complicated. So all this process really pays off when you are handling matrices with ranks in the order of hundreds of thousands, and you can reduce them to order of few hundreds. So after I found my matrix Q, I am going to form this matrix B, which is Q transpose A. And this is going to yield the low rank factorization of A, of my original matrix. And B is going to have rank 2K. And then finally, I'm going to compute the SVD factorization of the small matrix B. So the difference with the original SVD is that I am computing now SVD factorization on a way smaller matrix than my original matrix A. So I end up finding same decomposition, U sigma V, and then I'm going to set up U equals Q, this U tilde that we see here, and we're done. So this is the heart of randomized SVD. It works, it's really, really good for big matrices, and it's used everywhere in deep learning. So this is a very, very naive benchmark that we want to compare how SVD performs against a randomized SVD. So for NumPy, we have the classical SVD, and we are running this on a very classical example of tensor image representation. This is, it takes about 468 milliseconds per loop to perform SVD decomposition using classical SVD. And this is a small matrix. This is not a huge one. So just try to think how long it would take if my matrix is like 1,000 times bigger. TensorFlow SVD, it has implicitly randomized SVD. So it's not equivalent to NumPy SVD, and it shows 13.8 milliseconds per loop. And the scikit-learn has an implementation of randomized SVD that shows times that are really similar to TensorFlow SVD. So if you compare with the classical SVD that is implemented in NumPy, you see the order of magnitude of difference in the performance of randomized SVD. Okay, so that's all I have for randomized singular value decomposition. So all this looks good. So we were able to reduce the rank of our matrices to like orders of magnitude less than the original matrix. We are going to apply this to our inputs and to our kernels and to our weight matrices in our neural network, but we're still making a lot of matrix multiplications. All these operations that we see here are still matrix multiplications. So what's the gain? So there is this other algorithm that is called general matrix to matrix multiplication, GEMM. So again, matrix multiplications can stress even the fastest computers available, but GEMM is the fundamental building block for fully connected and convolutional, fully connected and convolutional layers mostly. And it's the most, I don't know if you have heard about general matrix to matrix multiplication before, but it's the most common numerical linear algebra optimization trick in deep neural networks, but you never hear of it. So it's like everywhere, and we're gonna see the details about it here. So I took this plot here from this paper, Computation Time Distribution of Individual Layers on an ImageNet Architecture. So what you can see here is that most of the time of GPU time or CPU time are spent in convolutional layers and fully connected layers. Mostly convolutional layers, if you see here. Pooling, not that bad, but convolutional layers and fully connected layers, they take all the time of our GPU or CPUs. So we're gonna see something here that is called arithmetic intensity. So it's basically the ratio of the number of flops or the number of floating point operations we're performing for matrix multiplication over the number of byte access. So if we have a matrix A n by k and a matrix B k by n, we see that for the matrix multiplication, we have m and k operation that's equivalent to the n to the 3 that we saw earlier. But it's going to require twice the amount because we are doing a multiplication and then a sum. So it's 2 operations. And the number of byte access that we have here is mk, nk, and n twice, because we're doing this twice. So this is the arithmetic intensity. So what we want to do here with general matrix to matrix multiplication is optimizing this arithmetic intensity. So we're going to show you with an example how GEMM works in convolutional layers, which are the most problematic and complex ones. So what we're going to show here is how we can approximate a convolution operation to a matrix multiplication and then using general matrix to matrix multiplication. So let's say that I have a 2D image, as we see here in the left. This is like any remote sensor or satellite image. This can be any of the ones that are available. And then we see here 3 channels. We can decompose these 2D image in 3 channels. So we have red, green, blue here. And but this is the case for RGB, but there are sensors that have, or like satellites that have many, many, many different channels, because they have not only color, but they have like near infrared, They have many other different spectra. So we can have, for satellite imagery, we can have tens or almost the order of hundreds of channels. And for other kind of imagery or data, we can also have like the depth of my original channel. My original input data can be really big. So the convolution, as we see in our right, is we have a kernel that is usually just a small kernel, square kernel that has like a size k. K would be the size of my kernel. And then I have my kernel the same depth as my original input. So the convolution is that I'm going to apply this kernel to each point or each pixel of my image and each pixel of my channels. And there's some other artifacts that are involved in convolution, if like strides. If we are going to strides, one is that we're going to apply the kernel to each pixel, or if we're going to leave some space between the application of the kernel. But let's assume that we're going to apply this to each pixel of my original input. So again, we have this input tensor of a number of channels, and we want to represent, the first thing we're going to represent is that we want to transform this ND array into just a 2D array and treat these as a matrix, as a 2D matrix. And we're going to do the same for the kernel weights. So in TensorFlow, Intel, MKL, QBLAS, using the data, like the specific data format for each of these implementations, we can represent these n-dimensional tensors into a linear 1D memory address space. And we're going to see how this is transformed in the next slide. So this data format, it's different in different implementations. In Theano, we have first the number of batches plus the number of channels, and then we represent height and width pixels in that order. In TensorFlow is first height and then width, and last is the channel. And it also depends if our implementation is optimized for GPUs or CPUs, but the idea is that we're going to represent ND tensor into just one vector, basically. So I still have enough time. Okay. So what we see here is that basically we're gonna transform the size of the kernel that we see here in red. We're gonna take the depth, the entire depth, and then I'm gonna make this sub-block. I'm just gonna represent this as a row using the data format of the implementation I'm working with. So we end up here with a matrix of h minus k plus 1, w minus k plus 1 rows, and dk columns. So when I see this n that we see here for representing in the same 1D way each kernel, the thing that I forgot to say is that usually we don't apply just one kernel to my input. Sometimes we apply hundreds of kernels. So that increases again the dimensionality of our problem. So what I'm doing here is representing this input image of size h by w with a number of channels, in this case d, depth. We're going to represent this as a 2D matrix, and we're going to represent my n kernels as a d by k, where k is the size of our kernel. So if you can think like, okay, if we are doing this for every pixel, we're going to end up with a lot of repeated data. So because we're applying the kernel to each pixel, so we're going to repeat data a lot. But this is going to pay off by the algorithm we're going to implement for the matrix multiplication. So the entire idea is we're going to optimize doing two things: representing convolution as a matrix multiplication, and then using something that we call partitioning. So this operation that we see here, like translating my ND tensors to these 2D matrices, is used, is implemented in TensorFlow as this operation into call. And this is just part of the documentation in TensorFlow's code, that like once we have assembled these image patches, like each of these red patches that we see here is assembled as a row, then we have finished it. We're gonna implement, as you see here in the bottom, we're gonna implement matrix multiplication of these patches times the filter, or in this case, the kernel in columns. And we're gonna get partial results of the output matrix. So that's the entire idea. We're gonna do something called partitioning. So what we're gonna do is approximate my original product AB with something that we call C, and we're just gonna choose patches of my input matrices, and we're just gonna start accumulating results in my matrix C. So we're gonna choose how many patches we're gonna divide our original matrices, and how we're gonna start accumulating results back into my C, my C matrix here. So it is very important to choose how many of these we're gonna choose, like the size of the patch is gonna be very important, as we see here, like this P value here is gonna be very important. So finally, what we want to achieve is that we can start doing these smaller multiplications in parallel. And we're just gonna start accumulating, like each of these partitions of my original matrices, we can perform these smaller multiplications in parallel and start accumulating into this resultant matrix C. So as we see here, I am sorry, we're using K and M and N and H and W everywhere, but let's get back to our original convention, because before we introduce the kernel size K, so back to original matrices, we have M rows, K columns, we have here K rows, N columns, and then what we're gonna do, we already represented this a tensor as a matrix. We are gonna assume our B matrix is our kernels, our N kernels represented as a matrix. Then what we're gonna just choose is we're gonna just choose tiles and start multiplying these small tiles and start accumulating these tiles into our resultant C matrix. And I don't think I have numbers of how much this accelerates matrix multiplication, but I can tell you it is very, 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 very important to use this general matrix to matrix algorithm, because you can keep all your cores busy and you don't have to do this serially for your entire matrix. You are just using blocks of memory to do these multiplications, and then you are accumulating your results into a big matrix. So to finish this idea, this is already implemented in most of the numerical linear algebra packages that are out there. So it's implemented in CUDA, it's implemented in Intel MKL, it's implemented in TensorFlow. So you don't really have to worry about implementing the details of general matrix to matrix multiplication. You can worry about decomposing your matrices using a randomized SVD. That's something you can definitely introduce. But general matrix to matrix multiplication, it's already implemented, it's done. We just wanted to show the details about how this is done. So I guess you're gonna have access to this presentation, but these are the main references. You can go and learn more details about this. The first one is basically the algorithm to approximate the matrix decomposition SVD using stochastic algorithms. So in this paper, you can find different approaches to how to choose your samples, if you're gonna just have IID independent samples, or you're gonna use something like a Gaussian sampler. So it shows you how, for each case, how the errors of your approximation are bounded and how much acceleration you can get from representing your matrices in these like low rank matrices. The second one, it's a very good paper, and it explains how you are partitioning your matrix to perform GEMM, and how GEMM is implemented even in lower blocks to achieve like fast and max performance. And the last two links are specific implementations of GEMM using Intel MKL and using NVIDIA's deep learning framework, basically QBLAST, which is the BLAST implementation for CUDA. So I highly recommend you to go and take a look at these papers and implementations, and to find use cases that you can use randomized SVD for both your data and your weight. And I think that's all I have. I think I utilized my full 40 minutes. So that's all I have for you. Thank you so much for coming to this talk.